All right, so when it comes to these circle parts, you can see here this big circle. You've got it on your notes. We've labeled different aspects of these parts. We've got our secant. We've got our chord. We've got a diameter, which again is a very special type of chord that goes through the center of the circle. You've got an example of a radius. You've got a center, and we've got a tangent. So all of these things are parts of a circle that are important for us to understand. And notice the tangent that's drawn is a ray. All right, it has one endpoint and goes on forever in one other direction, kind of like a beam of light. All right, so a flashlight has a light source and it shines out as far as it can go. All right, that will be like a ray. Okay, so now we want to be able to label these parts. So I'm going to pause the video here and let y'all try to label these on your own, and then we'll go over it. So the diameter is 2 times the radius. Okay, so the next little segment here has to do with tangents. Now, the relationship of tangents to 2 circles comes in a couple of different forms. First of all, we've got what we call a common external tangent. External means it's on the outside of the circles. In other words, if I've got 2 circles, the tangent's going to be on the outer side of both circles. It's not going to go in between. A common internal tangent is a tangent line that's going to go in between the 2 circles. All right? So you've got 2 different types of tangents in relationship to 2 circles. All right, let's go to the next slide. All right, so here we have a couple of examples. Now, in number 1, how many different tangents, and this is how it's going to be asked. It's going to say how many common tangents. Tell how many common tangents the circles have and draw them. All right? So, what's your question?
This thing is draw a line, right?
Yes. So, how many common tangents is number 1 going to have?
2.
2 common tangents? Well, let's see. We got a common internal tangent there. Common internal tangent there. Common there. Common there. So, how many?
4.
So, you got 4 common tangents. All right. So in number 2, can you go inside the circles to be a tangent? No, it's not a tangent if you go inside. So, whoops. So there are 2. Okay. All right. Now take a look at the next slide. Now do this one. Do these 3 on your own and tell me how many common you can have. Say what? Yes.
Which ones you can't? If you can't.
Oh, you go to the next one.
Okay. All right. So in number 3, Arvion, how many are there? Okay. So you got 1, 2. Can you have any more?
Yeah. What if you go between?
Is it?
Y'all told me that.
If these circles are not overlapped, yes. Yes. Because here's the thing. This tangent is an internal tangent that's tangent to both circles. It touches at one point on each circle, so it's on both circles. But those circles are not overlapped, so therefore it's not a secant. So it is a tangent. So you're right. All right. What about number 4?
1.
Talking about Gerlo. Number 1. I mean, number 4 is 1. Okay? So 3, 1. What about this one?
None.
Yep. Okay? There are no common tangents. All right? Look at number 5. Look at the next slide. All right, so this is a little bit more information about tangents. It says a line is tangent to a circle if and only if the line is perpendicular to the radius at the point of tangency. So here we have the point of tangency. If the radius makes a right angle, which means it's perpendicular, with the tangent line at that point, then we know that it is actually a tangent line. If it does not make a right angle, it's not a tangent. In other words, if it was like this, if it was just a little bit off to where it was not a right angle, it's not a tangent line. Okay? So it's got to make a right angle. To be a tangent, it's got to make a right angle with the radius at that particular point of tangency. Now, let's say that this is the point of tangency over here. Let's say this is the point of tangency. Well, yeah, it's going to make a right angle right there. Okay? But this was the point of tangency that we were talking about. So this is the tangent line at that point, and it's perpendicular to the radius at that point. So that's the definition of tangent. The formal definition, if you will. All right, so next slide. Is BC tangent to circle A? Now this is a problem that has actual measurements that we're going to do some math to prove whether or not, or to answer whether or not segment BC is tangent. So how are we going to do it? We're going to use something that we already know. If this is a right angle, then you know that this line, this segment BC is tangent. We have to prove that it's a right angle. What formula can we use? What theorem can we use for that? Pythagorean. Exactly right. So let's just do it. So we're going to confirm. So the hypotenuse is 26. So 26 squared equals 10 squared plus 24 squared. Let's confirm that this is a true statement. We're using the Pythagorean theorem to confirm or disavow, if you will, that it's not. It either is or it isn't tangent. So we're going to confirm it. All right, so 26 squared, I think it's 676. 10 squared is 100. 24 squared is 576. Guess what? These work. Let me make sure it's 676. It's either 676 or 656. All right.
It is.
Okay, good. All right, so it works. So we just proved that this is a right triangle. If this is a right triangle, then that angle is a right angle, and therefore, is BC tangent to circle A? Yes. All right. So copy that down. Okay, do the same thing in this problem. Confirm whether this is a right triangle or not. If it is a right triangle, we know that angle ABC, or angle B, is a right angle. So 27 squared was what?
729.
Okay, equals 16 squared plus 19 squared. 16 squared was 256. 19 squared.
360.
Okay, so these...
617.
Those are not equal. So therefore, the answer is no. If it's not a right triangle, it cannot be a tangent line at that point. All right, let's look at the next slide. Okay, do the same thing, except notice that we are missing a portion of this. Is BC tangent to OA? Well, guess what? We've got a missing part. That part is missing. But what is that part?
5.
What?
5.
No. How do I know what that part is? It's 5. Why?
Oh, because the other one's 5.
Because the other radius is 5. So if this radius is 5, that radius also has to be 5. So before you can do Pythagorean theorem, you got to know what that little segment is. It's 5 because this segment's 5. So what is 5 plus 8? So now you can do the theorem. So do that. And that's what? And then 5 squared plus 12 squared, 25 plus 144, 169 equals 169. So that checks. So yes. All right, have you already done the next one?
No.
All right, so if you haven't done the next one, go ahead and do that one.
Yes, sir, yes, sir, yes, sir.
All right, so you can see the answers there, and it is yes. We had to fill in the 10 for that radius. So let's take a look at the next slide. All right, so here we have another situation. Now, what we just looked at really was not, didn't really require a whole lot. We just had to confirm using the Pythagorean theorem that it was either a right triangle or not, which made the line tangent or not. But here, we're dealing with what's going to become a formula for, or a theorem for us, if you will. All right, a rule. Tangent segments from a common external point are congruent. Now, common means it's the same for both. External means it's on the outside of the circles. So, these two segments are coming from the same point and they are both tangent to the same circle, which means that these two segments are congruent. They are the same. So we can apply this to some problems. So look at these two problems. The first one, you got 2x plus 7 and 31. What do I know about these two expressions? They are the what? They are what? What? Who said it? What'd you say? Say it again. I can't hear you. What do you know about these two segments, guys? Say what? Thank you. They are set equal to each other. They are the same. So since they're the same, hey, since they're the same, 2x plus 7 equals 31. So then you just solve the equation. I'm not going to, y'all can solve that. Look at the next one.
How you do that?
Solve it. Look at the next one. X squared and 36. Are these the same also? Yes. So you do x squared equals 36 and you solve it. So how am I going to solve this? Square root of both sides. Exactly. So go ahead and solve those. On these, I'm asking you to give me x. So to do x, you subtract 7 from each side. 2x equals 24. Divide by 2. X equals 12. Now, I could also come back and ask you to plug that 12 in to give me the length of the segment. But do I really need to do that for this problem? No. Because I already know it's 31. Okay? But if I had two expressions that had variables, like 2x plus 7 where it is, and then x minus 8 right there, then I would need to plug it in to find the length. Okay? All right. Now, on this one, since it's a quadratic equation, we have to take the square root of both sides to undo that squared part. So that gives us x equals 6. Okay? So square root of 36 is 6. All right, go on to the next slide. All right. So here we have radius, radius. We got this portion here, 4. We got this portion, 8. We don't know what r is. We don't know what the radius is. So we're going to have to set up an equation. Now, how are we going to set up something? This kind of goes back to the previous problem. We've got to set up something using Pythagorean theorem. All right? So, r is the variable. Okay? We don't know what r is. R is the radius. We don't know what it is. But we can set up an equation to solve for r. Here's how we're going to do it. Pythagorean theorem. Pythagorean theorem is going to be hypotenuse r plus 4 squared. No, we're on Thursday schedule. Equals r squared plus 8 squared. What I just did was set up an equation for r using the Pythagorean theorem. Now, there's going to be a little bit of work to this. On the left side of this equation, we've got the square of that binomial. Well, how do you do that? We use the FOIL method. Y'all remember the FOIL method, right? First, outside, inside, last, right? So I'm going to write it. I'm going to expand it out. So we've got r plus 4 times r plus 4. That's what it really means. So I need to multiply the first terms together. R times r is r squared, right? R squared. All right, and then I multiply the outside terms. R times 4 is what? Then I multiply the inside terms. 4 times r is? Then I multiply the last terms. 4 times 4? 16. Whoops. Alright. Now, that's going to be equal to the right side, which is r squared plus, what is 8 squared? 64. Alright, so, now here's the thing. I need to simplify a little bit. What is 4r plus 4r? It's 8r, right? So I'm going to put those two things together. So I'm going to bring down the r squared plus 8r plus 16 equals r squared plus 64. All right. Now, it still kind of looks ugly, but it's about to look pretty. What is the rule when you have the same thing on both sides of an equation? They cancel out. So I've got r squared on each side. So what can I do? I can cancel out those r squareds. So now it's a basic equation. 8r plus 16 equals 64. So go ahead and finish that out. Go ahead and solve that on your own. So Marlon, we just
How about 8?
pretty easy, yes.
Alright,
So we're going to subtract the 16, and then 8r equals 48, divide by 8. So our radius equals 6. So we were able to find what the radius is. So there you go. Now that was a little bit of work. That's the longest problem we'll have. Of all the problems that we do, this is the longest. Because it requires you to use the FOIL method
Wait a minute.
and then solve an equation like that. Say what? Yep. Alright, let's go to the next slide. Okay, y'all do this one on your own. It's the same type of problem, but I want to see you do it on. Alright, so there you've got the answer. The radius is 12. Okay, very good. Questions? Alright, so here's another one. Do this one.